Where is this message is not coming? Okay. Okay. Now only it's coming. And then share screen. Okay. So before I begin, I just wanted to I just wanted to request you, if some things are anything that is discussed in the class is not clear, please speak up. You can speak up either during the class, in which case I'll try to repeat it during the live interaction, or you can message me. Like you can, I don't know how you will do it, but if you collectively have if 10-15 of you are don't understand or don't follow a concept that is being discussed, please message me in WhatsApp. We can have a separate, now a completely informal interaction where we can actually, instead of me speaking monotonically, we can have a discussion so that it helps to bring clarity to the concepts. The idea is that I don't want even a single person to go out of this course without grasping the fundamentals. The equations and other things will follow, but the fundamentals is what is more important. I know that these kind of concepts have not been introduced in your undergraduate for the master's MSc students. They have not been introduced, especially the ones which we are going to do now. Please try to be with me in case there is a problem, in case there is, because if it's all sequential, if you don't follow the first one concept, the next one will be even more difficult, and the next one you will be completely lost, and then after that you will kind of lose interest in the whole course. Okay, I don't want that to happen. Okay, so that's why I'm kind of repeating. Even a recap actually is used. I see it as a use to I use it for kind of making sure that the concepts are clear. Okay, so having said that, we will go to the current potential. So that's my sincere request. Please take it as a request. Try to see what you can do from your end. If there is anything not clear, please let me know. Okay, so the rate of the reaction. So this is our interest was in the rate of the reaction, because the rate of the reaction in a heterogeneous, under the conditions of heterogeneous electrified interface. Electrified interface. So what is the rate of the reaction? That is given by the standard definition of the rate at which the product is formed with respect to time, and that n here, because it is a Faradic system, we apply Faraday's laws of electrolysis, and then say write this n as Q by Nf, where n and f are constants. This is the Faraday's constant. Faraday's constant, which is basically 96,500 coulombs approximately. And this is the number of electrons involved in the redox process. So that gives us this concept of dq by dt, which is nothing but the rate of change of charge, which in our conventional definition points to current. So the overall rate of the reaction you see is directly proportional to the current in the system, and because n and f are constants for a given system. Say for example, if we talk about Fe2 plus going to 3 plus, or Fe3 plus reducing to iron, or any redox reaction, the number of electrons transferred is going to be a constant, and Faraday's law constant is itself a constant. So the rate of the reaction nu is going to be directly proportional to the current in the system. Now, just to bring in the additional clarity or additional uniformity in the system, what we say is that instead of representing the rate of reaction in a conventional kinetic sense, because we are talking about a heterogeneous electrified interface, we normalize it to the area of the interface, just so that we know that anybody who does for the sake of uniformity, because I do a reaction with 1 centimeter square interfacial area. The interfacial area meaning that it's an electrode-electrolyte interfacial area, and somebody else sitting in Gujarat does it at 10 centimeter square per electrode. The rate of the reaction should not change. That means If we don't normalize it, then the current will be different because it depends on the area of the electrode or area of the interface, and therefore you would apparently be mistaken that the rate of the reaction is changing because we increase the electrode area, which cannot happen. So the rate to bring in that constant of or bring in that uniformity factor, we normalize it to the surface area the in terms of centimeter square, and then we say that I by A is what is current density. So this current density, this parameter, what we do. So now the nu is becomes directly proportional to J across all systems. And now what we also saw in the last class is that this, for an ideally polarized electrode interface, you see that any change in delta V, as long as delta V is less than the IPE range of the system, your current change is going to be very small, approximately equal to 0. That's because you have a saturating behavior. You have a saturating behavior, and this is actually the behavior that we discussed in the ideally polarized electrode interface. The exponential part on either side is the contribution from the relaxation time constant from the new CT. So this steady state current, steady state current that we see here is indeed the steady state current that we observed in the case of cyclic voltammetry, cyclic CV on IPE. Remember that argument? So what is this? This, we said that the voltage with respect to time varies in a triangular fashion with a scan rate plus nu and minus nu, and then it again goes by plus nu and minus nu and so on and so forth. And then we saw that the rate, the current is going to be this exponential growth is going to depend on the relaxation time constant tau, and then followed by saturation, which is the steady state current, and then going back to this behavior. If I plot it as current in term with respect to voltage, remember all this? Yes. So that is the steady state current that that is represented here. But when it comes to an ideally non-polarized electrode interface, what you see is that it is called, in other words, it is called a leaky interface. Leaky interface. The term leaky means that whatever charge you try to bring into the electrode surface gets automatically leaked onto the electrolyte side, or vice versa. It could be that whatever charge that is coming from the bulk to the electrolyte interface is automatically leaking onto the electrode. Either way, basically the charge doesn't want to stay on the surface. It either goes into the solution or goes to the electrode and thereby comes out of the electrode at the other end through the circuit, through the external part of the circuit. So this means that because we are talking about the current, the charge when you put it on the electrode immediately leaks to the surface. That means that the current which is measured across the interface is going to vary. So even for when you change the delta V by a very small amount, very small amount, dV, then the current change is going to be significantly higher than 0. Okay, the current change. So this basically, this is V here. Okay, let me not confuse you with E. Okay, so so even for a very small change in delta V, the current actually increases very steeply. Okay, I wouldn't say what way it is increasing. I'm just only going to say qualitatively that it is increasing very steeply. And this is a typical behavior of an ideally non-polarized electrode interface. Is this clear? We looked at, this is basically a summary of what we did last time. Is this clear so far?
Yes.
Yeah. Okay. So now we will look at, so our idea is, now that we have an handle, we have come to this important conclusion that the rate of the reaction, when I say rate, the kinetic rate of the reaction is going to be proportional to the current density. Okay, the current density that we measure in the system. So now what we need to understand is what are the parameters that affect the reaction rate. Just like how you would do in a chemical kinetic system, what is the rate going to depend on? It is going to depend on concentration, it is going to depend on temperature, all these things. But what is the relation? instead of qualitatively saying that this is a it is going to increase with the rate of the reaction is going to change with increase in temperature or with increase in concentration, because you know the rate law. That is a very qualitative argument. In case of an heterogeneous electrochemical interface, what are the factors that govern or affect the reaction rate? That is what is the primary question that we are going to address in the next at least 4-5 interact 4-5 hours. Okay, so now before we get into the actual discussion, we need to understand, let us take a simple model system, say Fe2 plus going to Fe3 plus electron. This is a typical oxidation process that is happening. So that means, and this happens at an interface. Okay, we have put an interface. Now because this is an oxidation reaction that you want to do, your anode, the oxidation happens at the anode, so the electrode that we have put in is an anode. And it is, we also know that oxidation can happen when you oxidation means, go back to the definition of oxidation, it involves a electron transfer from the species in solution to the electrode interface. That means the energy of the interface, the electrode side has to be significantly going in the positive direction. So I maintain a positive polarity on the electrode interface on this anode, and this positive means that automatically there is a cathode sitting at infinite distance. We are not even bringing the cathode into the picture. Cathode sitting somewhere, some corner of the system. With respect to that cathode, this anode is maintained positive potential. Okay, so that's why I have put positive here in the on the anode. Is this clear so far? So I'm just repeating myself. So the reaction that we want to do is an oxidation reaction. So when we want to do an oxidation reaction, first thing that gets fixed is the interface has to be involve an anode. The electrode electrolyte interface has to involve an anode, because we are talking about an oxidation reaction. And what should be the sign of the anode? The anode should be positive with respect to the cathode. We are right now, the cathode is not there in the picture, but we know that by very definition, you change the energy of the electrode either in the reduction side or in the oxidation side, but that change is with respect to some electrode, some other electrode sitting somewhere in the same system. So we are not bringing that second electrode here. We are, because we are, it is complex enough to look at one interface. Forget about looking at two interfaces simultaneously. And besides, anything that is the concept that we are going to discuss and put down for this interface equally applies to the other interface also. It is just that the signs are going to be reversed, but the concept, the core is exactly the same as if we discuss for one interface, the other interface is going to be the exactly same core concepts that are involved. So now, because we are saying oxidation, we have said that taken the anode side, and again, because it is oxidation reaction, the anode has to be maintained positive with respect to the cathode. So that's why you're being put in positive. Now we know that from our discussion on the non-Faradic part earlier, midsem, pre-midsem. So please recollect that. You can't lose that. Okay. What we see is, if we create a positive charge, the first thing that happens in the electrolyte side is that negative charge species. These species again can be one of the three between ions, naked ions, or solvent molecules. Any one of these species. Okay, I should not have written this. Let me just erase this, because there is going to be some. Okay, so let me. So this ion from the electrolyte side can be ions, naked ions, or solvated species with the appropriate polarization, solvent species. Okay, this is solvated ions, naked ions, or solvent species with the appropriate orientation. If it is water, then I would expect this, because this has a negative polarity, so that means I would expect this to be the orientation of the water molecule. But essentially, these species try to approach the interface and build up the double layer. Yes, that is very clear. Now, in this stage, we are not even talking about ion 2 plus or ion 3 plus or anything of that sort. Okay, in this stage, if we freeze the system, we can write the direction of the electric field. The direction of the electric field is conventional direction is from the positive terminal to the negative terminal. So we put the electric field vector as starting from the anode and going towards the cathode. Is this fine? I'm going very slowly in very small steps. Please let me know then and there. Stop me. Ruthlessly stop me, please.
Subbu, I have one question.
Yes.
Here we want to oxidize, say for example, iron 2 to iron 3.
Hmm.
Uh, so iron 2 is a cation. Uh,
Hmm.
and if we want to oxidize this, anode is positively charged. So how do
Hmm.
we specifically adsorb iron 2 on the interface?
Exactly. That is what is going to be the rest of the story, dear. I'm very happy that you have figured it out before I started it. It is going to be a trick, or that is what exactly is going to form the rest of the story. You'll get your answer, yeah, in 2 minutes.
Okay.
Thank you so much. That means you are totally with me. If you have already got that question, if anybody has already got that question with them, then that means they are totally we are on the same page. That's the next question that I'm going to ask.
So I think this is possible because we have said here that anode is positive with respect to cathode, but
Huh.
we have not mentioned that anode is always positive.
No. See, with respect to the cathode, or see, the idea is you lower the energy of the system. It has to accept electrons from the species in the electrolyte. It has to accept electrons. Now, the problem is how do you bring in Fe2 plus, which is positively charged, to a positively charged, or to a see, when I say it's positively charged, that means it is depleted in electrons, right? It is electron deficient. So you are now talking about bringing a cation which is positively charged to an already electron deficient surface.
Yes,
That
yes,
seems to define logic. Okay, seems to define logic. You are already having a surface which is depleted in electrons, and on top of it, you want to bring a cation which is positively charged, which is also depleted in electrons closer to it.
yes,
Okay, so that is the crux of the question, the real crux of the question. I'm so very happy that some you guys are with me. Okay, this really indicates that we are on the same page. Now let us do that. Let us try to do that. Now this let us take an Fe2 plus because this is our reactant species. Now this is present happily in the bulk. Now you are lowering the energy of the electrode. You are shifting it to more and more positive potentials. Anode, you are now shifting. It doesn't happen immediately. You have to go down below the thermodynamic potential of Fe2 plus. Now, when you start approaching the thermodynamic potential, what is going to happen is this: what are you trying to do in the system? The first, if you want to look at this reaction as a series of steps, this iron 2 plus going to 3 plus plus electron, as a let us now deconstruct this simple oxidation reaction into a series of steps. First thing that you need to do is from the bulk, it has to mass, the iron 2 plus, which is happily sitting in the bulk, has to mass transfer, has to come close. When I say mass transfer, it has to migrate closer to the interface. It has to migrate closer to the interface. Okay, then once it is at the interface, there is a negative, remember there is a negatively charged species lining up on the electrical double layer. It has to break through that, because unless it is there at the interface, you cannot do this reaction. The Fe2 plus oxidation to Fe3 plus cannot happen even if it is say 510 nanometers close to the surface. It has to be really close. The distance of approach of the cation to the electrode interface should not be more than 1 or 2 nanometers. Only at that distance can this reaction happen. If it is 5 nanometers and say that okay, on a atomistic scale 5 nanometers is close enough, can we hope the reaction would happen? No, it will not happen. Okay, so it has for not only if the so the first step which we are considering is moving that or pushing Fe2 plus from the bulk to the to closer the to to a region which is close to the electrical double layer, then it has to penetrate the electrical double layer and that adsorb, this important word, adsorb on the interface. Only if it absorbs, then thermodynamic energy, if the anode is positive enough to accept that electron from the Fe2 plus, that means we have to keep, see, going in the reverse direction also means that you are changing the energy of the anode. Okay, you are decreasing the energy of the anode. So you are now the anode, you have decreased the energy to such an extent below the thermodynamic energy required, such that now the process of accepting an electron from Fe2 plus becomes favorable for the anode. So that means Fe2 plus goes over to Fe3 plus on the surface. It is an adsorbed species. This Fe2 plus is an adsorbed species which actually converts to another chemically different adsorbed species called Fe3 plus. That is our oxidation. In the process, the electron is pushed into the interface. And thermodynamics tells us that Fe2 plus to Fe3 plus, if you write the E naught of this half cell, this say some x millivolts, this tells us only the energy that is required for this. No other energy is being specified in this. No other energy is being specified in this. Okay, so we will come to that. Okay, we will come to that. Don't worry about the energy calculation now. So let us try to understand, and basically we are deconstructing this in this reaction. So first mass transfer, then a very important step which is adsorption, then followed by oxidation. Okay, where the electron gets transferred, and now you are converting Fe2 plus through another chemically different, electrochemically different species, which is Fe3 plus. Okay, which is still adsorbed on the surface, because only the Fe2 plus which is adsorbed can convert. So suddenly when you form Fe3 plus, it cannot go directly into the bulk. What is required is this Fe3 plus now has to be pushed out. So just exactly opposite, from the adsorption you go to a desorption. And then Fe3 plus, now not only when I say it is desorbing, that means it is moving out from the surface. It is still not into the bulk. So you need to do a mass transfer again to get it back into the bulk. And this, once it comes into the bulk, only then do we say that this conversion of Fe2 plus to 3 plus is complete. The oxidation of Fe2 plus to 3 plus is complete. So this simple reaction that we have written in one line here is a complex set of events where you have two mass transfers, one towards the interface, one away from the interface, an adsorption and a desorption, again one oriented towards the interface, another oriented away from the interface, and then a conventional oxidation, which we know that is where the electrochemical conversion happens. Okay, now in this, with this picture, if you look at every single one of this process, the electric field, the vectorial direction of electric field continues to exist. There is no change in that. The electric field continues to exist. And what is the direction of the electric field? It is starting from the anode and going towards the cathode. It is going from the left to right of your screen. And now what becomes obvious, very obvious, is that if we have an Fe3 plus in the adsorbed species, desorption, the direction in which this Fe3 plus ion needs to transport in order to reach the bulk, and the direction of the electric field that we have created in the system are parallel. That means the desorption of the Fe3 plus from the surface to the bulk is in fact assisted by the electric field. But what has to happen before that? The mass transfer and the adsorption events of Fe2 plus from the bulk to the interface is in fact happening opposite to the direction of electric field. That means the electric field is going to oppose the first this transport of this the reactant from the bulk to the interface, whereas the electric field favors the transport of the product from the from the interface to the bulk. But then the one important thing you need to also remember is that because you are saying that one case it is opposing, another case it is for favoring, doesn't mean that the net energy required is zero. Because it is once you initially you are talking about Fe2 plus going to the surface, which is being opposed by the electric field, but this is a completely electrochemically different species in the form of Fe3 plus that is desorbing and moving to the bulk. So because these are electrochemically completely different species, you cannot do a balancing within this circle itself and say that okay, I don't have to talk about energy. That means you cannot say that okay, Fe2 plus to going from the bulk to the for this mass transfer step, I need an energy E1 because it is direct. Maybe I'll write it as epsilon 1 to not to confuse with this. So this is energy required, energy epsilon 1. Okay, so that means I need what this step, this Fe2 plus mass transferring to the to closer the to near the electrical double layer, that requires, that is an action that is going against the direction of the electric field. So that means I need to spend energy to do this step. That energy that I spend on the system is energy E1. It doesn't stop with that. The Fe2 plus has to break through this double layer and absorb. So this absorption energy required, let me put it as E2 or epsilon 2. And then this Fe2 plus getting converted to Fe3 plus is this thermodynamic energy. Thermodynamic energy. This is what you get from the table. Only this energy is what is known to you from the table. You don't have any idea of energy epsilon 1 or epsilon 2. Now, and this epsilon 1 plus epsilon 2 is the energy that is input into the system, energy input into the system, because if you are interested in doing this reaction, you necessarily has to provide this energy. That energy has to be on top of the thermodynamic energy. Thermodynamics requires a certain quantum of energy, but this energy input that you're doing in order before thermodynamics can take over is the additional energy input that you need to do to the system, or additional work that you need to do to the system. And then, but intuitively, let's say the desorption energy. So now this desorption energy is E3. This is favored by the direction of electric field. Similarly, the mass transfer energy E4 is favored by the the electric field. But what is important is because E1 and E2 are with respect to Fe2 plus and E3 and E4 are with respect to Fe3 plus, which is chemically, electrochemically, every sense different. You cannot say that E1 and E2, the energy that I put into the system, which is E1, E2, is going to be equal to E3 plus E4. That doesn't happen. E1 plus E2 at no stage, I'll put a very strong can be equal to E3 plus E4. That means essentially, and in fact, I can write a second relation which is going to be E1 plus E2 is always going to be greater than E3 plus E4, because the energy required here is minimal. You have already set up the direction of electric field that favors the desorption of the species and moving it to the bulk. That already favors. So the energy that you spend in doing that, in moving the Fe3 plus from the interface to the bulk, is going to be very minimal because the direction of the electric field favors it. But before that, the direction of electric field opposes each of this mass transfer of Fe2 plus to the and then for absorption of Fe2 plus to the surface. So that means E1 plus E2, the energy input that you're doing is definitely significantly greater than E3 plus E4. And what E1 plus E2 has to be done on top of the thermodynamic energy. It is not that if it's not sufficient if you do only E1 plus E2. Once this absorption happens, you also need to provide the thermodynamic energy in order for this oxidation to happen. Is this clear? I've covered, like I've told many different things. Anything that is not clear?
Subbu, please repeat the E2 part.
E2?
Yes, yes.
This one?
Yes, yes, Subbu.
Okay, so maybe I'll let me just see. E2 part repeat means you just want to know about the adsorption, or you want me to
Yes,
repeat?
yes.
Okay, see, once what is important, we need to take it for species from the bulk to the interface. To somehow it has to come to the electrode surface. Okay, now we do it in two steps. One is it takes it to till the electrical double layer. That is called the mass transfer step. Okay, because you're transferring a mass from the bulk to the interface, to closer to the interface. And then once it is at the interface, you have a species, negatively charged species lining up, because this is the nature of the interface, the double layer itself. This 1 nanometer separation is going to be composed of this double layer, which we saw in the non-Faradic part. And then what we need to do is we need this Fe2 plus needs to break through that. If like it needs to, it's like an armor. Okay, it's like a shield. This electrical double layer is like a shield, because essentially, even while describing the electrical double layer, we told that the whole purpose of EDL is to shield the electric field from the surface to the bulk. So it is shielding. So this shield has to be penetrated. Fe2 plus has to penetrate the shield before it can see the interface, see the electrode surface and get adsorbed. Okay, that is the, so for that the system cannot supply energy. We need to externally supply that energy, and that adsorption energy that we supply in order for this Fe2 plus, which is close to the interface but still has not at the interface, to break through this double layer and locate itself at the interface or the electrode surface. That adsorption energy is what we call as E2. Is this clear?
Okay, I got it.
Yeah. Anything else?
So this energy that we need to supply E1 plus E2
Ah.
before the reaction can happen,
Hmm.
uh, I'm guessing is it what constitutes overpotential?
Exactly. We're coming to that. We are coming to that. Yes, yes, yes. Slowly. I don't want to take up that term before you actually understand the concept. Okay. I don't want to. We can. I could have easily said it is a over potential, but I want this. I prefer to go this way and then finally reveal. You spoil my suspense. But
Sorry
yeah,
about.
that's what. No, no, no. That's you're right. That's ultimately going to be the over potential. We will see that. We will see that. Okay, so things are clear so far. Okay, so then,
Yes.
yeah, so then let us look at another reaction. Okay, so in this case, this is also an oxidation reaction, but here it is a zinc going to zinc 2 plus plus 2 electrons. Zinc metal, which is at the interface, going to zinc 2 plus plus 2 electrons. Here again, you set up the same, because it's an oxidation, it is an anode, and it is positive with respect to cathode. With respect to cathode. Okay, all the governing rules exactly same. So you line it up, you make it electron deficient, and then you have now, instead of some species coming from the bulk to the interface, the reactant is already available at the interface. In fact, the reactant is the electrode itself. You have these zinc ions lining up on the surface. So now on the surface bound zinc ion is zinc atoms are going to leave become Z. So this each one sphere, if it is Zn, this Zn is going to go into the solution as Zn2 plus zinc cation, and in the process the two electrons are transferred, or it's, if you think of it very crudely, the two electrons are left behind by zinc 2 plus. Well, that's not the picture. It actually, this is a very complex set of events. The end result of that is you have the surface is now having two electrons excess. Okay, so if this is the situation, then zinc 2 plus is, for whatever formed, has to form at the interface only. Now the point is, you don't need to bring in the reactant, you only need to desolve the reactant, and in which case the cation, the zinc 2 plus which is formed, is supposed to move in the direction of the electric field. The direction of the electric field also doesn't change because you're doing an oscillation, positive to negative. So now the movement of the cation that we are interested in, the zinc 2 plus, is now desorption and mass transfer. Both these processes are happening in the direction of the electric field. So what essentially we want to by going by these two examples is that the electric field, if you create an electric field at the anode, it hinders the movement. Any movement of cation towards it is unfavorable or is resistive in nature. Okay, the system tries to resist, the electrode or the interface tries to resist the movement of the cations towards it, and rather it and consequently, or in the going in the same continuous line, you can also infer that the cation movement away from it is favored by the electric field. So the electric field now here is becomes partial. It becomes partial, saying that if you want to take a cation away from the interface, I'm going to help you. But if you want to bring in a cation towards the interface, I'm going to oppose it like anything. So it is now the same electric field has now assumed a kind of a partial or a bipolar characteristics, in the sense that it is going to favor one set of process, it is going to resist another set of process. But if you take this example of Fe2 plus to 3 plus, without actually going through the resistive pathway, it is impossible for you to go to the do the reaction. Without having to spend this energy E1 plus E2 onto the system, energy spent to the system on the system, without having spending that energy on the system, it is impossible for you. Although the second set of events are favorable, if E3 plus going to the bulk is favorable, that is never going to happen unless you supply energy E1 plus E2 plus the thermodynamic energy. Is this clear? Is this clear?
Yes, Subbu.
Okay, so then that is what we are talking about in terms of overpotential. So what essentially this electron transfer, if you want to generalize this, say O plus Ne go into R, this is a reduction reaction. So if you want to generalize this, or you can, everywhere there is a reversible reaction, reversible arrow that is put, because it can be O going to R or R going to O. The same set of events is going to happen. The electron direction of the electron transfer at the interface is going to be different. So if you want to take this O, it is from the bulk. You have to go through a mass transfer, then an adsorption process. Then this O adsorb converts to R adsorb, which basically then goes through desorption, then a chemical reaction, and then followed by mass transfer again back to bulk. If you want to take the other way around, then you can let me not take this. Let me take this. So if you start from R, your reactant is R, then you go, R goes to bulk, the surface, and then a chemical reaction happens. Then an adsorption happens here, electron transfer happens, and then followed by desorption of O to then followed by chemical transfer, and then mass transfer back to O. So you either follow the red or the blue, doesn't matter. It's the same, more or less the same path. The energies required are going to be different, but the path is the set of events that has to happen one after the other. If either O goes to B, O goes to R, or R goes to O, the set of events that happens in a sequential manner is essentially the same. And now what we saw is that if for going back to this example of Fe2 plus going to Fe3 plus, we need to spend E1 plus E2, this amount of energy we need to spend on top of thermodynamic energy, because thermodynamics by itself for this conversion of Fe2 plus to 3 plus requires a certain amount of energy. But here, because we want to do it at the interface, we have to end up supplying this energy E1 plus E2 on top of the thermodynamic energy. And that E1 plus E2 is what we call as overpotential of the system. That is what we call as over potential of the system, denoted by eta, which is basically the E that you end up the energy or the potential in electrochemical symbols. Whenever you're electrochemical terminologies, whenever you are talking about either energy input or energy output from the system, it is always in terms of potential, right? Energy input to the system, you add or you change the potential of the system. Energy taken out from the system is going to be in the form of potential difference. That potential difference driving a current through externally, that is a different part. But what the system is going to either ask if it is requiring energy or supply if it has excess energy is always going to be in the form of potential difference. So we are writing this over potential, that energy on top of the thermodynamic reversible energy. So this irreversible is the thermodynamic energy that is required for that particular conversion, no matter what conversion you're talking about, thermodynamic energy requirement. This comes because you are forced to do it at the interface. So that means the difference between this total energy required, because you are doing it at the interface, which involves mass transfer, adsorption, desorption, all these processes, which can act either in favor or against the electric field. You have to necessarily spend a certain amount of energy on top of the thermodynamic, in addition to the thermodynamic energy, and that excess energy that you are spending on the system is what we refer to as over potential, because by the definition itself it is called potential on over which you need to supply, the thermodynamic potential over which you need to supply to drive the reaction in the system. So like I said, we have just written the same argument in a general manner. First, mass transfer to the interface. The second, adsorption at the interface. Electron transfer, for which means that the reaction is happening, followed by desorption, and then followed by another mass transfer to the bulk of the product to the bulk. Or this means product. Okay, so all these 5 steps have to happen. Okay, and automatically you see what is the thermodynamic energy is the reversible Nernstian value. The reversible Nernstian value, which you can pick up from any table. So you have to supply energy on top of the Nernstian energy required. That means this process or this route of where you need to supply energy and thereby deviate the potential from the Nernstian picture, because Nernstian is going to be exact. Even if you hold the potential at irreversible thermodynamic potential, you are not going to see anything happen, because one set of events will exactly balance the other set of events. So your net reaction is going to be zero. So what we say is purely just like what we saw, what we discussed here, that the electric field is partial to the reaction. Although it is just one reaction that is happening, one half of the electric reaction, that is Fe2 plus from the bulk to the interface, is resisted by the electric field. Other half is actually favored by the electric field. So the electric field is partial towards the reaction. Okay, towards the process of the reaction, and that's why we call this as a polarization of the interface. Remember, in the EDL case, we called it as electrification, because there is no reaction that is happening. It is purely electrified interface. Here we call it as a polarized interface, because the electric field that you are creating at the interface is partial or polar to the reaction that is happening. So that essentially drives us to the deviation of the electrode potential from the reversible Nernstian value. That is what is called as the over potential. Is this clear?
I have one question. So
Yes.
if the electrode were ideally non-polarized, then the overpotential for any species would be zero, is it?
Exactly. The whole world is trying to make an ideally non-polarized interface electrode, because that means you don't need to spend this excess energy. But unfortunately, there is, just like how you see, there might be an ideally polarized interface, at least for a small voltage window, it is there. But there is nothing called an ideally non-polarized interface. Nothing. So what does an ideally non-polarized interface means? You supply exactly the thermodynamic potential, the reaction will happen. There is no need for mass transfer, no need for adsorption, desorption energy, and so on and so forth. That electrode is that such an interface is not there at all so far. It's absolutely not there. Is that fine?
Yes.
Subbu,
Yeah.
I have a doubt. Like, if we apply the over voltage,
Hmm.
excess over voltage,
Hmm.
so in case of iron 2 plus, it will going to oppose the Fe2 plus more strongly as compared to the normal reversible voltage.
Yes, that is true. But then see, you are not only doing this positive trend, but you are also see by making this more and more electron deficient, that see there is a certain electron deficiency associated with iron 2 plus. Now, if you make the system more electron deficient, then it is like with respect to Fe2 plus, this becomes more electron deficient, and therefore this movement is favored. That
So
is
that
how
is
you need.
regarding the molecular orbital level. Uh,
Exactly.
okay.
Okay. Now, okay, this is the block picture. Okay, so far things are fine. So now the last point that I want to briefly mention, or not briefly, point out here is that see this over potential, as long as you want to drive this reaction, no matter which O2R or R2O, no matter which reaction, any reaction at an interface, you as long as the reaction has to persist, you have to necessarily keep supplying the over potential. You have to pay that penalty. It is not as if that you pay the penalty, okay, I will start the reaction, I will pay the penalty and then go back to thermodynamic value, the reaction will stop. Okay, it is not like kickstarting an engine, you have the spark plug, you provide a lot of energy for that spark plug to ignite that fuel, and once that is happening, that energy itself, a part of the energy that is generated, is spent in re-spent or recycled or kind of rerouted to burn in more fuel and therefore getting more energy. That cycle will not happen. Here, over potential is a persistent demon. Is a persistent demon. That means as long as you want to maintain that reaction, as long as you want to drive that reaction, you need to necessarily keep spending over potential. So it is essentially the potential penalty, the penalty in terms of energy, which is in electrochemical sense potential, required to sustain current in the system. That means what does current indicate? Sorry, what does current indicate? It means that the current is nothing but the rate of the reaction. We already saw that current or current density is the rate of the reaction. So rate of the reaction. So that means as long as you want to keep a non-zero rate of the reaction, you need to keep spending this potential penalty. The moment you cease the penalty that you are paying, the current will drop to zero. The reaction will not happen, will cease to exist. So at this stage, I just want to, do I have time? Oh, I'll just stop. Maybe I'll stop here and I'll continue it with the example in next class, because I want to anyway repeat the example in the next class. Okay, so I'll stop here. Is that fine?
Subbu, I have a question.
Yes, please.
So we don't have ideally non-polarized interface,
Hmm.
right? So that is because of the electrical double layer that is formed, because it has to cross that penetrate that double layer,
Hmm.
some ions, right?
Yeah, even otherwise, there is a mass transfer involved. See, observe, if you say that, okay, I remove my entire double layer, okay,
Yeah.
even then you are not sure whether the reactant is there at the interface or not.
So if we take like fused salt rather than the aqueous,
Hmm.
so is there any chance of getting the non-ideally polarized electron?
No, even then, see, you can take fused salt. You can people work with a lot of fused salts, fused sodium chloride, magnesium chloride, and so on and so forth. That means molten sodium chloride and magnesium chloride. Even there, you need to spend energy because it is not really adsorbed.
So that is regarding the mass transfer.
Hmm. So we will see. See what is bound to happen is if you want to lower your mass transfer your energy that you spend in mass transfer, you will automatically increase your adsorption energy. It's a trade-off that you will do. We will come to that. It might look like uncoupled events. Right now, the way we have discussed, mass transfer is decoupled from adsorption, desorption, which in turn is decoupled from electron transfer. You will once we start discussing more and more on this, because the rest of the major part of the course is only about overpotential. I'll keep referring to that. So you will see different types of overpotential. One, if you want to lower, if you try to lower the mass transfer overpotential of the system, automatically the adsorption overpotential will increase and so on and so forth. We will see that. It's a trade-off. So you can never have a zero overpotential. Zero overpotential is basically an ideally non-polarized interface.
Okay.
Okay.
Yeah. Okay.
Yeah. So shall we stop here and we'll continue the tomorrow. Okay. Tomorrow we are meeting at 10 o'clock. Please. Where is this? Okay. Stop sharing. Thanks a lot. Tomorrow we'll meet at 10 o'clock. I promise we will take a break. I can't go for more than 45 minutes or 1 hour. So we'll take a break and do it slowly. Okay. Yeah. Thanks.